And the parametry was something he wanted to for slides, so then he went to go to work on event horizon telescope data. So he went for his PhD at the Max Planck Sleep Radio in Bonn, where he was working with Dr. Friedbaum on the formation of jets and imaging, constructing images of jets with the event horizon telescope. So this is what he's going to talk to us about today, because he recently defended and got his PhD from the University of Cologne. Thanks for being with us, Roland.
Thank you for the introduction, Calliope. So yeah, today I'll talk about what I did in my PhD for the last 3 years, which is dealing with millimetre VLBI. We were looking at the source 3C84. Here's a brief outline of what I'll talk about today. So I'll start with talking about AGN observations with millimetre VLBI. Then I'll move over to an overview of 3C84. I'll talk about our results, which include an analysis of the core shift and the magnetic field. We also looked at the VLBI components and the kinematics. And then I'll finish with an outlook and the conclusions of our work. So, as you know, active galactic nuclei, or AGN, can launch jets. This is what you see in this illustration on the right. We have a dusty torus around a central black hole, which ejects the collimated jets from the poles. You can also see some sort of winds structure here, originating from the torus. The radiation that we get from AGN stems from synchrotron processes and inverse Compton emission, which is from the jet and it's non-thermal radiation. We also get free emission, which is from the dust and thermal. And what we measure with our radio telescopes around the world is the synchrotron emission. Here's a brief outline of the model that we usually assume. The classification of the different AGN that we have in the literature depends largely on the viewing angle. If we look straight into it, this would be this line of sight here. We observe what's called a blazar, and this can be, for example, a flat spectrum radio quasar or be a lac object. But if we are slightly off-centered from this immediate line of sight, for example, if we look at it that way, then we can have what's called a von Arok-Rayleigh galaxy. But the classification also depends on the luminosity, and I list here two important equations: the Eddington luminosity and the bolometric luminosity. And depending on this classification, we have radio loud galaxies where we see the jet, and also radio quiet galaxies. Depending on this luminosity, we can have, for example, Seyfert galaxies, which I mentioned because, as we will see, 3C84 is one of those galaxies, called the Seyfert 1.5. Now, as I said, the AGN is the powerhouse of the galaxy, of the radio galaxies that we see. Here's an illustration of what we would see if we had perfect resolution. We have, of course, the black hole in the center and the disk around it, and we have the wrapping of the disk that is an apparent effect of gravity. And we also see the Doppler boosting, like if it's moving towards us, it should be brighter on that side, and when it recedes, it should be less bright. Of course, there's many open questions still. For example, we still don't know exactly how the coevolution of the mass of the black hole works together with the evolution of the galaxy. We also don't exactly know the connection between supermassive black holes and the spins. And also, for example, which exactly is the metric that describes all of this. To tackle this, we use very long baseline interferometry called VLBI. As you can see on the left, we have this radio source, for example, a jet, which is emitting the synchrotron radiation. And here is a simplified example. I only show two telescopes on the globe, and what each of them measures is the radiation. And if we combine this, we get this fringe pattern, which is the response. And this is described by this equation, which is theta, which is the angular resolution. This is proportional to the wavelength of the observation, and also the baseline, which is the distance between the telescopes and the globe. We want to minimize theta to get a better resolution. So this can be achieved two ways. Either we increase the baseline, and then we have to go to space, because the distance between two telescopes on the Earth is limited, but if we go to space, we can get larger distances. Or we can decrease the wavelength of observation. And here, for example, I show an array that we use at 3 millimeters, called the global mm-VLBI array. And in our work, we chose to go with the latter. So we used mm-VLBI, which offers a number of advantages. With mm-VLBI, you can peer through the densest self-absorbed regions. You can explore the physics of the central engine. You can study the origin of jets, and zoom into the heart of radio galaxies, achieving typical spatial scales of less than 0.1 parsec, or a few hundred to 1,000, 10,000 Schwarzschild radii. Specifically with the GMBA, we get excellent UV coverage and high dynamic range, as you can see here on the right. And to guide the eye, I'm plotting here a circle and the radius of what a telescope would be if it had the size of this simulated array, of the simulated telescope that we have. So this array corresponds to a telescope with a radius of 9,000 kilometers. Of course, we can also do synergy with other instruments. We can do spectral studies and look simultaneously at, for example, 7, 3, and 1 millimeters. Or we can do broadband multi-wavelength campaigns. For example, combine our radio observations with X-rays using, for example, the Chandra satellite, or do gamma ray analysis using Fermi. As I said, we use the global mm-VLBI array. Here are the locations of the telescopes around the world. When we observe, we use the Effelsberg 100-meter telescope, which is close to where I work in Bonn. We also sometimes go to Spain to use the 30-meter telescope, but there are also other ones around the world. Here are some highlights of this array. I know this slide is a bit crowded, but the point is that you see that there's a lot going on, and this is just in the past few years. So you can imagine that there's a lot going on. And now let's focus on the source of my work, which is 3C84. So 3C84, or the host galaxy, which is called NGC 1275, is pictured here at higher frequencies. On the left, we have an optical image. What you can see here is and the velocity of the emission line, and most strikingly, you can see these filaments around the core, which are supported by the magnetic field. And on the right, you can see an X-ray image of the source, and overlaid are the contours of the VLA. So these are radio contours. And what you can see, interestingly, is that we have these two what they call X-ray bubbles, which is the absence of X-rays. So the darker blue ones, and they correspond to the contours of the radio jet. So that's where the jet passes through. So we can see that there's definitely some interaction of the jet with the intercluster medium. What's also interesting is that, as you can see, the bubbles are off-centered from the jet axis, which might point to some sort of rotation, as we will see. Now, let's zoom further into the source. So on the left, again, you can see NGC 1275, which is the central galaxy of the Paraschos cluster. It's an elliptical Seyfert 1.5 galaxy, as I mentioned, also Fanabar-Riley 1 galaxy, and overall peculiar. And it has estimates of the central supermassive black hole mass of up to 2 billion solar masses. If we zoom in further, this is with 22 gigahertz round-based VLBI, you can see a beautiful two-sided jet and the central core, of course. And what's also interesting is that there seems to be some filaments connecting the plumes to the central region. If we use space VLBI, we get to the right image. So here we use a satellite with a radio astron mission. And as you can see here, the central part reveals the southern jet part, which is clearly visible. And two other most striking features, which you can also see if we just zoom a bit further into the core. So you can see these two limbs here, this double rail, which is pronounced. This is called limb brightening, and this is also seen in other jets. But most interestingly, you can see that the core is elongated in the east-west direction, and this is perpendicular to the bulk jet flow. So the bulk jet flow is in the more or less north-south direction, but the core is elongated perpendicular, and naively you would expect that everything should be streamlined. So in my work, we wanted to investigate what this can be. Now this core elongation is also visible on the left side in polarization. So this is at 86 gigahertz. And I drew this parabola to guide the eyes to see that it goes very deeply into the core. But you should keep in mind that the polarization is very variable in the source. So on the right, this is 43 gigahertz. And as you can see, it's just 1 month apart of each other. You can see how drastically it changes. But this is not an effect of instrumentation. This is actually intrinsic to the source. So jet launching, acceleration, and collimation are still open questions, which are fundamental to jet science. And radio galaxies, such as 3C84, provide a prime test bed to explore the jet base and the black hole location. Specifically for 3C84, look what the origin of this east-west elongation is that I talked about. Could it be a broad jet base, jet bending, or something stationary like a collimation shock? And also look at the kinematics of the ejected components. We investigated the jet launching speed, the acceleration of the components, and whether there's non-ballistic motion at play. So here I show an illustration of what the core of 384 might look like. We have again the dusty torus around the central black hole and the collimated jets, which are ejected from the poles. This, as you can see, this jet is well collimated. And this would correspond here to the left side of the panel, which is called the Blandford Znajek type of jet. In this jet scenario, this jet launching scenario, we have a very thin jet, which is very fast. However, it could also be that the jet is launched on the disk, and then it's broader. It's the central part of the panel, which is called the Blandford Payne type of jet. Or, more realistically, in our opinion, we can have a stratified combination of the two, where you have a slower outer sheet and a faster inner spine. So a combination of the two scenarios. So without further ado, we can look at the results. First, we wanted to investigate what the black hole position is relative to this elongation, and to try to explain, perhaps, using the position, what we are observing. Our first strategy was to do a spectral index map to see if we can get some insight into the nuclear region. Here is what we might expect to see. So this is just a cartoon. I should also mention that our definition of the spectral index is as shown there. So the flux is assumed to be proportional to the frequency of observations to the spectral index alpha. So starting from the top and going clockwise, if we have a uniform disk with a black hole at the center, we expect that there is no spectral index gradient, and the spectral index should be rather flat, so around 0. If it's an edge-brightened jet with the black hole at the center, so a Blandford Payne type of scenario like I showed in the previous slide, we expect that we have a gradient starting from the center and going towards the outside. On the other hand, if it's a north-south oriented jet, we expect a spectral index gradient in this north-south direction. If we have a recollimation shock, so the black hole would be, for example, to the north side, we expect, again, the absence of the spectral index gradient, and the spectral index would be a little bit negative. And finally, if we have a bent jet, so the black hole is, for example, on the west side, and we saw it, then we expect the spectral index gradient in this east-west direction. So first, we'll use quasi-simultaneous observations of 3C84 that we had at 15, 43, and 86 gigahertz taken in the same month in May of 2015. On the left, you can see the spectral index map at 43 to 15 gigahertz, and on the right, 86 to 43. If you look at the central part, the core part, you see that there is indeed a spectral index gradient robustly detected. And if you look to the high resolution image on the right, you can see that it starts at around 2 in the north and goes to around minus 1.5 in the south. But this is just one epoch. So we wanted to see how this behaves in other epochs. We had data at both 43 and 60 gigahertz over 10 years. And here I'm showing where it was possible to actually do spectral index maps. As you can see in the 6 epochs, we again robustly detect the spectral index gradient, but it seems to turn with time. So it seems to start out in the north-south direction, but then it seems to turn into a more east-west kind of orientation. And this might point to the fact that there is jet rotation. Then the next thing to know about VLBI is that the absolute positional information is lost. So we get what's called a core shift. So that means that when we see the observation in the sky, we don't know exactly where it is. What we can do is assume that we have a homogeneous and conical jet, like I'm showing here. And then, depending on the frequency, the core that we see, which is not the actual black hole location because of opacity effects, we see it at a distance of the real core, which is the cartoon at the top. So if we have a low frequency observation, it will be further away. The higher the frequency, we see the core closer to the real location. And again, this is because of opacity. It's not something real. The first way to find how much the core shift is to do a two-dimensional cross-correlation between the maps that I showed you, so 1543 gigahertz and 4386 gigahertz, and to see what the maximum of the cross-correlation function coefficient is located in the spatial map. So again, this is 1543 and 4386 gigahertz. And based on the location of this, we can plot where the core is at each frequency. So again, we have 15, 43, and 86 gigahertz. Now, since we don't know absolute positions, we have to set one of them arbitrarily to 0. So we set 86 to be at 0, and then we can see compared to 86 where 43 and where 15 is. Again, I'm illustrating here that we have a jet, the jet apex here, and the distance between the geojet apex and the core increases with decreasing frequency. That's also how I'm plotting the observations of the observing frequency. What we can do is we can fit a parallel of the form I'm showing at the top, which then is this fit. And then we find that the 86 gigahertz core is located around 80 microarc seconds north of the south of the real VLBI core. And I can show you how this looks like. So this is the left panel. You can see the contours of the 86 gigahertz. You can see the core position at 15, 43, and 60 gigahertz. And extrapolating, like I showed in the previous slide, you can see that the real jet apex is located here, which is this distance, the 80 microarc second that I mentioned. However, since we only had 3 data points, we tried also a second method to be more certain of our results. This is the middle panel. So what we did here is we took 6 epochs of 86 gigahertz over a time range of around 7 years. We stacked it, and then we fit to the jet opening a parabola, which is the dotted line, and a cone, which is the continuous line. And we have the apexes of both. So this N1 is the parabola, and N2 is the cone. However, here, the fit did not prefer either of the 2 positions. So we had to go a step further, which is the right plot. This is very busy, so I'll go try to explain it in detail. So this is a plot of the bulk Lorentz factor versus the viewing angle. And as you can see here, we have two types of lines in there. The continuous lines correspond to the jet to counterjet ratio. To find the jet to counterjet ratio, for example, for the parabola, we take a line which passes through N1, we sum the flux north of it, we sum the flux south of it, and we take the ratio. And we also have the dotted lines, which corresponds to the apparent speed of the components. This we get from the literature. As you can see, these lines cross each other, the dotted lines and the continuous lines. Now, based and we get the two positions, N1 is again the parabola, and N2 is the apex of the cone. These are the two shaded regions. Also, then looking at the literature from our paper and the pencil paper, we can get a position of the velocity of the components as well as the jet to counterjet ratio. And then it seems that N1 is closer to this measurement from the literature, which then points to a jet apex being at N1, so that the parabolic fit is more likely. So then the jet apex is not very far away from the center of the 86 gigahertz measurements. Overall, combining these two, we can find that the jet apex is 200 to 1,500 Schwarzschild radii upstream of the 3 millimeter VLBI core. There's also an alternative approach, which is not based on VLBI. And here we use the variability of the source. So if the source flares, which are the peaks in the variability light curves, then depending on the frequency of observation, this flare will appear first at higher frequencies. So this is 345, 230 gigahertz. This is 37, 15, and the gamma rate. But now let's just focus on the radio flex. So the bottom four ones. You can see that first the flare is visible at the higher frequencies, and as time passes, it starts to get visible at lower frequencies. And this time difference can be translated into distance, and then again one can do a fit of where the jet apex is located. To calculate the time lags that I mentioned, we used two methods. This is the work that we did with Vasilis together. And the one on the left is using discrete cross-correlation, this DCF. So we just correlate the two neighboring frequencies to each other and then find the time lag between each frequency pair. But we also used Gaussian process regression, which is a machine learning technique, to fill in the gaps between the frequencies, and then again measure where the peak of each flare is, and then again calculate the distance in time between them. We get this plot, which is similar to the one I showed before, but here instead of the distance on the y-axis, we have the time lag. The two different symbols correspond to the Gaussian process regression, the open symbol, and the filled-in symbol is the discrete cross-correlation. As you can see, they agree very well with each other. We can again fit this and get an estimate of the power law index of the fit, which is around 1, as you can see, and this corresponds to equipartition. Using this, we can calculate the magnetic field strength and its topology. So again, we assume that we have a conical and homogeneous jet, and also that it's synchrotron self-absorbed. Then using this formula here, which seems complicated, but in fact only two are the important measurement quantities: the omega, which is the core shift that we measure, and the alpha 0, which is the optically thin index, which was measured. And then using this, also the kappa is the one is equal to 1, like I showed you in the previous slide, then we can find that the magnetic field at the extrapolated jet apex is 2 to 4 Gauss. Then we also wanted to compare it with other nearby AGN, so we extrapolated it to 10 Schwarzschild radii, and we find that it's at 10 Schwarzschild radii 70 to 600 Gauss, which compares well with M87 and NGC1052, which are similar nearby radio galaxies. We also extrapolated it to 1 parsec, and we see that it is 0.06 to 0.2 Gauss, which is 4 to 6 times lower than in BLX and quasars, which indicates possibly intrinsic differences between 3C84 and the sources. Then we also wanted to look at the topology. So again, the assumption that the magnetic field drops as a power law with a power law index B, then B is given by this formula, where, as I said, K is the power law index of the fit of the core shift analysis. Alpha 10 is the optically thin spectral index. Then using n equals 0.42, n is the power law index of the distribution of the number density of the particles. And this 0.42 is a measurement that we get from the literature measuring the opening of the jet width. And Kr we found with our analysis yields a power law index for the magnetic field equal to 1.7, which points to a mixed configuration between a toroidal and a poloidal magnetic field. Now, the next thing to do after we looked at the core region was to look at the jet morphology. Here's how the jet looks like at 15, 43, and 86 gigahertz. These are stacked images of the jet over 10 years. And you can see the jet ridge line. So this is where per slice where the jet has the highest intensity. You can see that at 15 gigahertz, there are two prominent regions, the core and this region, which is usually referred to as C3, is a brighter knot. At 43, it's more visible, the core is more visible, and the C3 region is less pronounced. And at 86, I'm zooming in to show that there seems to be this double ray structure that we also saw in the space VLBI image. Then we wanted to look at the profile of the jet. So we took transverse slices to the ridge line that I showed you, again at 50 and 43 and 86 gigahertz. And as you can see, to fit it, we mostly need two Gaussian profiles. So this seems to again confirm that we also see this double rail. So it's one Gaussian plus another one on top of each other. This points to jet stratification. So on the left panel, you can see a plot of the width of the jet and the y-axis and the distance from the core. And as you can see, at different frequencies, it seems to change. So at the lower frequencies, it's more or less around 0.3, whereas at higher frequencies, it's 3 times as much. So this might indicate that at higher frequencies, we see the central region, and at lower frequencies, we see the outer sheath. And this is also confirmed by the right plot, which is again the deconvolved width difference between 1543 and 4386 gigahertz with a distance from the core. As you can see, it is mostly positive. So this means that the jet gets narrower the higher the frequencies. Then we looked at the jet kinematics, so the components which are ejected from the core region. This for this source, we already have data from the 90s. So kinematical studies were already carried out 30 years ago. So we have a large data set to compare to. Here are all the epochs that we use. So on the left side is the 43 gigahertz observations, and I'm just focusing here on the core region, where we were able to identify 6 different components. And on the right side, we have the 86 gigahertz observations, where we have data from 1999 all the way to 2020 for this work. And here we were, of course, able to identify way more components, both because we have more observations, but also because we have a smaller beam, so we are able to differentiate between more components, which at 43 gigahertz would be on top of each other, and it wouldn't be possible to differentiate between. So here I'm showing the central result of this work, which is a plot of the distance between and the time. And what we have here are 5 components which we were able to cross-identify both at 43 and 86 gigahertz, which I showed in the previous slide. They are color-coded, so F1 is the darker one, all the way up to F5, which is the lighter colored red one. And the filled-in symbols are 86 gigahertz, and the empty symbols are the 43 gigahertz. What we find is that in the core region, the components move subluminally up to 0.1 times the speed of light. This is achieved by fitting a linear regression to each component. We also see that newer components, so everything right of the red line plotting, seems to move quicker. And also at 86 gigahertz, so at the higher frequencies, it seems like components move marginally faster. This is a 2-signal detection. And here I'm just showing what we assume, so that in the beginning we have a pointing flux jet, which we cannot see, and then it broadens and we see this double ray, which we then can fit with a linear regression, and the components also, in this source at least, accelerate further downstream. Now, we also again looked at the variability of the source. This is all the data that we have reaching back to the 1980s. And again, let me remind you that the color coding is the 5 components that we were able to cross-identify at 43 and 60 gigahertz in the previous slide. So we wanted to see if the broadband flux density is associated with the component ejection. But let's go from left to right. So on the left, we have this component called W1, and the shaded region shows where it was approximately ejected, plus its error bar. So as you can see, it corresponds to the total intensity maximum that we have for the source, which was in the 1980s. And if we look at the position of this component, and we look also at its trajectory, then we can identify it with this circle region I'm showing here. It's also called C2 in the literature. This is a diffuse component of this source. And this is the first time this component can be associated with a feature in the total variability light curves. So I think it's fascinating that we can look 40 years into the past and draw conclusions of the source using this technique. Then let's go on the right. We have F1 and F2, which are the components that we were able to cross-identify at after 2010, where we have also 43 gigahertz observations. Unfortunately, we do not have a millimeter flux data. So this is millimeter, this is centimeter radial flux, and these are the gamma rays, which we'll look at in a bit. So we don't see any feature in the centimeter radial flux. However, if we zoom now into the more interesting region where F3, F4, and F5 are, we can see that F3 seems to correspond to the onset of the flare in the radial flux, and the same goes for F4. But F5 seems to be on the decay of radial flares. Now, if we look at the gamma rays, it seems to be the opposite. F3 and F4 seem to be on the decay of flares, and F5 seems to be on the onset. So it seems like for this source, we cannot give a conclusive answer of the relation between the component ejection and the flares, the features in the variability light curves. To get a better understanding of what we see, we tried to cross-correlate the radial flux in the millimeter and the gamma rays, which I'm showing here. So this is 230 gigahertz and 345 gigahertz and the gamma rays. And positive and negative time lags, as you can see, so negative, positive, indicate that there's multiple emission regions along the jet. A positive time lag here means that the gamma rays are trailing the radial flux. I should point out that the gold dotted lines correspond to the 99.97 confidence level. So at 345, it seems to be a bit below, but at 1 millimeter, so 130 gigahertz, we have definitely robust detections of both peaks. So, as I said, this might indicate that there's multiple ejection regions. If the gamma rays precede the radial flux, then it will be upstream. However, if they are after the radial emission, then it might be explained by some turbulence in the downstream jet region, which perhaps causes mini jets, which is then the source of the gamma rays. Another thing that we did was to look at the average flux at the time of ejection of components, and then see what velocity they turned out to have. As you can see, there's a trend here, which is increasing. So this indicates that components which turned out to move faster were ejected during periods of higher flux levels. And this, again, might be indicative of jet rotation. Now, if we look at the flux density versus time, for example, here I used the 37 gigahertz light curve, where we have a lot of data starting from the 80s. You can see that there seems to be a trend which looks like something periodic. The overall trend is what I'm talking about. And if you also look at the position angle of the inner jet, which is the red line, you see that it seems to turn with time, and this might also align with this overall periodicity that we're seeing. Then people have also noticed this and tried to simulate the periodic motion of the jet. And this seems to be consistent with a precessing jet model with a period of around 12 years. Now, if we put all this together, we can explain everything if we have a rotating helical filament inside a broader jet sheath, as you can see here. This will explain the spectral index time variability that we saw, the trajectory of the different jet components, the jet stratification, the velocity increase of components when they were ejected during intensified flux, and also the minima and the maxima that we saw in the light curve. This is what I have been doing in my PhD. Now, currently, we want to see with our own data if we can improve on this, because all of this was archaic. I have been using the clean algorithm for this, which has a number of advantages. It is consistent with images for good UV coverage. It runs fast and is robustly tested, but also has some drawbacks. It is suboptimal for resolving extended structures, and it also requires data to be phase calibrated. So what I'm trying now is to use regularized maximum likelihood methods, or RML, which provides a continuous image representation, so you get better resolution. It's primed for scripting, so you can automate things. It also offers forward modeling, which allows for more flexibility. It has drawbacks, of course. It's slower, and its convergence highly depends on the correct initial assumptions. So this is still preliminary. It's what I'm working on now. So using RML, this is again at 22 gigahertz for 3C84. You can see that the limb writing that we saw continues all the way down to around 5 milliarc seconds. The jet structures seems to exhibit kinks, and this is also consistent with the jet rotation assumption. I also wanted to show a couple more sources that I've been looking at. This is an array of 150 and J0102 plus 58. And it's interesting that with RML, as I said, we can better image diffuse emission. So besides the core region, which is usually seen using clean, you can see these diffuse structures which seem to propagate further off from the jet. Before closing, I also wanted to just show one slide of the outlook. I think it's very exciting that our work is the basis for verifiable scenarios with our own EHT data. For this MPI of 2 epochs, one has been observed and one will be observed, hopefully in a couple of months. And with the EHT data combined with the GMBA data, so 1 millimeter and 3 millimeter observations, together with lower frequency ones, we will be able to discriminate both via direct imaging, spectral index mapping, and colorimetry. If we have, as I mentioned in the beginning, a Blandford Payne type of jet with straight steep spectral index, if there's a disk shock, a disk or a shock in this elongated structure with a flat spectral index, or if we have a curved jet with an east-west oriented gradient. And here are some simulations of what we might expect to see. And with that, I arrived at my conclusions. So we demonstrated in this work that we have the capability with millimetre VLBI to resolve jets transversely in nearby radio galaxies. For TC84, we found that the jet apex is 200 to 1,500 Schwarzschild radii upstream of the 3 millimetre VLBI core. We found that the spectral index gradient orientation is time variable. Same goes for the position angle of the inner jet. The magnetic field of the jet apex is 2 to 4 Gauss with a mixed toroidal configuration. We found subluminal motion in the core region with near components moving faster and acceleration towards the parsec scale jet. And we find a lack of strong correlation between radio and gamma rays, which might indicate that gamma rays are likely emitted from multiple locations. And I'll leave it at that. Okay, questions.
I was wondering about the last point, because I was going to ask you about this. Yeah. How do you draw that conclusion from the data you show?
Mostly from the discrete cross correlation between the millimeter radial flux and the gamma rays. So we have 2 peaks, so we picked a double Gaussian to be able to locate the exact position of the peaks, which I should also say are in agreement between the 2 frequencies. So since one is positive and one is negative, the positive means that the gamma rays are trailing, so they are before the emission of the radio, and the negative one is the opposite.
Yes, that I understand. But
Okay.
Showed earlier in a previous line, showed that the gamma ray emission is
So as you can see, there are 3, I would say, major peaks, but there's also some lower peaks. So it's not clear if this goes first and then this, or if this goes first, then this, and then that's where the peaks come from.
It's not a clear.
No. But I have gotten the question before, so I want to point out that we think they're correlated, but we don't know which comes first. It's not that they're not correlated. Yeah.
So could you explain a bit more about the spectral index that you mentioned at the beginning, and why do you expect, for example, to have alpha approximately 0 when you are talking about this plot again?
Yes, because let me go to the slide. So if there is no jet and there is no synchrotron, then we don't expect to have opacity effects. So we expect that the flux should be the same in all frequencies, giving a flat spectral index.
would it have a secret zone from thermal electrons in the grid and thereby have most absorption and optical spectra as well?
We don't expect to be able to see that at least in the 4396 gigahertz. If we have the EHT data, we might be able to see some more structure there. So this also we confirmed this with simulations.
Thanks, Lou, for the nice talk. Very interesting results and many results. I have many questions, so you have the chance to talk after tomorrow.
Sure.
Stay here.
We'll talk better today. Yeah. I'm leaving on Wednesday.
Just a few things. So how do you conclude that the magnetic field is a mix between the
Yes. So in the slide. Yeah. So it is based on the simple assumptions, the magnetic field would be toroidal if B would be 1 and apoloidal if B would be 2. So since we find that it's 1.7, we assume that it's a mix.
But this R is the distance from the black hole.
Yes.
The scaling doesn't what we are talking about is cylindrical distance. So
Is what? Sorry.
is the cylindrical distance. I mean, you expect that the B is inverse proportional to the distance, the cylindrical distance, if it's toroidal, and the inverse proportional to the cylindrical distance square if it's
yes, toroidal.
Yeah.
Exactly.
So it's not the same mark. So
No, yes, like you said, this is the
it could be, for example, along the axis of the tree, and the shape of the Z is parabolic with the power law, let's say 2 over 1.7. It will be consistent with the 1 over r squared.
But the shape of the jet.
Yeah, that's the same because you can calculate it, you can find it. You say that it's parabolic.
Yes.
So what's the exponent in the parabola?
Yes, in the parabola, I think it's -2. I think. Yeah.
The assumption is that the Z is quantified, because otherwise this expression cannot follow for the parabola. So the B parameter comes up only if the Z is quantified.
Yeah, but
In order to apply this,
it's independent to find the same by modeling the link brightening feature, and you did that very well.
We took the slice, the perpendicular slice to the jet, but in the core region, it's not yet cylindrical. It's either parabolic or conical, depending on the assumption and the.
If it is parabolic, then you find the exponent of the expression Z proportional to R to some power.
I am aware of a paper, I think it's 2021, that they did it and it changes, but yeah, that came out after hours, but I can calculate that and see what comes out.
These are independent. Something else. We are talking about the rotation. You link the rotation with the axis of the is the period of rotation consistent with the binary black hole in the same model?
There are people who claim that, however, we're not convinced if it is rotation, it is precession and not notation. So we think that notation is more likely because 12 years is too fast for jet precession.
Okay. So rotation, yes. Base.
Why is 12 years too fast?
I think the explanation is because it is not it is too massive to do that.
You have two quick ones. First, you said that in VLBI, from service before,
Mhm.
almost always in the picture.
We see the core, what we call the core in the VLBI terms, we do not see the jet apex. Yes. And we don't see it because of opacity. What can be done is to do astrometry to have absolute positions, but for this source it has not been done, so that's why you have the portion. But in theory, if we do astrometric measurements, you know exactly.
Why didn't you do this?
Well, these are archival data, so it's not mine.
And the other one was about the algorithm, and you said that you developed such that between the different structures, and I was wondering what would be different.
No, this I didn't develop it. I'm just trying it out.
But what is the concept?
So, yes. So far, the results that I presented, which are from my PhD, are with the clean algorithm, which you know, yeah. So if you do RML, it's Bayesian. So you give an assumption of the sky, you give an assumption of the source, and then it tries to converge given those things. So you don't have individual delta components, you have something continuous, which fits better the diffuse emission.
But they want to know in advance.
Yes. It's not perfect, but it gets better results for diffuse emission. Mm. And you can get better resolution because you don't have to convolve it with a beam.
Going back to the paper motion presentation.
Mhm.
So you said that the figure is estimated to be 20 years.
Yes.
So given that you know how this only talking about the international black hole, what would be the radius in these that would justify these predictions? So how far away from the black hole this relation between
I have not done the calculations. However, I think it is of the of the magnitude of the core shift. So it would be a few thousand Schwarzschild radii. However, that is what I want to do, because also if you look at this that I'm showing now, I want to see if this king structure, so this, and this, if it will correspond to this time frame of 12 years, and that's why it does this kings. That's on my current list.
Of course, this rotation period
Mhm.
is not exactly the plan, because as the blood goes away from the source,
Mhm.
the rotation increases. So it's not exactly the same.
And also there's an interpretation that it is precession, and these people find 100-year period. It's just that for us it doesn't seem to be consistent with our data. We have higher frequency data, they use lower frequency data to find this. So
but anyway, the light it said it only covers a minimum 1 billion. So you can
Yes.
easily claim possibilities.
Mhm.
That's what I'm going to say.
Can you explain again how you estimate the Z1 Z ratio?
Yes. So we have the two apexes at the parabola and the cone. We draw a line which passes through it. We sum the flux north of the line. We sum the flux south of the line, and we take the ratio. Here you will tell me that there's not much flux yet. So for this region, we yes. So we used an upper limit from the RMS.
Let's send it over to them. Unless there's questions on mine, wait, sorry.
If there are any questions from the people online, just unmute yourselves. I don't see anything.
So you're the rest of the day.
Mm.
Thank you.